Hello friends, so for today's questions of the day we have a few related to the polarity stuff we talked about yesterday and then a couple things about bond length and bond strength that I just want to make sure we've talked about at some point. So first up was just identifying the hybridization of the carbon atoms in this molecule. We have two carbon atoms, they are both the same. We can see that there are 2 electron domains around the left carbon, 2 electron domains around the right carbon because reminder, triple bond still only counts as 1 electron domain, so both of these carbon atoms are sp hybridized. We were then asked which of the following has zero dipole moment, so we need to be familiar with the vocab term dipole moment. Dipole moment is just a measurement of polarity, so if something has zero dipole moment, that means it is nonpolar. So the AP exam is not likely to ever come out and just tell you this molecule is polar, but they might tell you this molecule has a dipole moment of 0.46. The number is not important, but what you need to recognize that if it's not 0, it's polar. If it is 0, it's nonpolar. And the larger the number, the more polar that thing is. So this question is asking us which of these is nonpolar. So if we draw out the structures for all of these and consider their molecular geometries, we can figure out which of these is going to be the nonpolar one. So in the first one, we have a linear arrangement of our atoms, but only one of our bonds is polar. Remember that carbon-hydrogen bonds are considered nonpolar. So we only have one polar bond pointing in one direction. So the polar bonds are arranged asymmetrically in this molecule. There's only one on one side, which means that it would be polar. In NH3, all of our bonds are polar, but the geometry is trigonal pyramid, which means all of our bonds are kind of pointing in the same direction. That lone pair makes the molecule take on this pyramid shape. So in the orientation I've drawn it, all of our bonds would be kind of pointing down-ish. Note that just for the purposes of clarity, I drew all of my molecules more or less in the shape that they would actually be, but that is not a requirement. Lewis structures are not intended to convey geometry, so you do not have to draw a bent molecule with a bend in it. I just did so it's a little bit easier to talk about why this is polar or nonpolar. So same idea applies to the next two ones, SO2 and NO2, both have a bent geometry. Note that NO2 is a little bit weird because you do end up with an odd number of electrons. It's not something you come across very often, but essentially on this one, when you're going through your usual Lewis drawing process, you fill up your peripheral atoms' valence shells and you end up with 1 electron left over. So instead of throwing a pair of electrons on nitrogen, you just throw a single electron on nitrogen. That does mean we cannot quite fill its octet, but we want to bring it as close as we possibly can. So this nitrogen has 7 valence electrons around it that it is sharing with oxygen, along with this 1 that it has full ownership of. We would still consider that a bent geometry. So again, we have polar bonds kind of pointing in the same direction, not completely distributed around our molecule. So these first 4 options are all polar. The last one was the correct choice, because although we have polar bonds, and in fact every bond in this molecule is polar, they're completely evenly distributed all the way around the central atom. So this is completely symmetric, meaning that it is a nonpolar molecule and therefore has a 0 dipole moment. So PF5 was the correct choice on that one. Next up, you were told that BF3 is nonpolar, but NF3 is polar, and you were asked to explain why this is the case in terms of molecular structure. So in a question like this, a picture is worth 1,000 words, in my opinion. If you can draw a picture and point to something on it to make it easier to explain, that is 100% allowed and encouraged on the AP exam. So rather than trying to just describe in words what is going on here, just drawing quick Lewis structures for both of these, I can easily point to the fact that this has a lone pair on it. NF3 has a lone pair on the central atom, And that is what is affecting the geometry. That because I have this lone pair here, that makes my geometry a trigonal pyramid instead of being planar, creates that asymmetry in the molecule that is making it polar. Whereas BF3 does not have that lone pair on the central atom, so it's going to be completely symmetric. It is a planar molecule, meaning that it is going to be nonpolar. So pointing to this one has a lone pair and this one does not is the, in terms of molecular structure, piece of the explanation, and how that relates to the geometry and how geometry relates to polarity is what we were looking for in this one. Do make sure that when you're asked to compare two things like this, that you do mention both of them in your explanation. So if you just said NF3 has a lone pair on the central atom, so it's asymmetric, you're not like contrasting that against how is it different from BF3. It's kind of implied, but you should be explicit in your explanations. This one has a lone pair and that one does not, and this is why it makes a difference. So whenever you're asked to compare two things, do make sure you talk about both of them to some extent. It doesn't have to be a lot, but they should both be mentioned in your explanation somehow. Alrighty, so that takes care of kind of the stuff we talked about before. Onwards to some new and different things. So this one was probably a little overwhelming to look at first. That's fine. But I think if you really stop and think about what are my axes here, what do these words mean, you can start to figure out the meaning of this graph at least a little bit, even though you've never seen something like this before probably. I know I don't show these in Chem 1. But the way the axes are labeled, internuclear distance, is very literally the distance between nuclei, the distance between two bonded nuclei specifically. So that is essentially our bond length. On the y-axis, we have potential energy. Potential energy is related to stability. Stability is related to the strength of attraction between two things if we're looking at, two particle interactions, which we are here because we're looking at the distance between two nuclei. So in general, the lower something's potential energy is, the more stable it is. If we're looking at an attractive force, that means the atoms are more strongly attracted to one another, or whatever particles are more strongly attracted to one another. So looking specifically at this type of graph, they always have more or less the same type of shape. And the important point here is the energy minimum. So the energy minimum is where those atoms are most stable. So the distance to that most stable point is the bond length. Essentially what this graph is showing is if you take two nuclei, and I usually imagine them starting far apart, essentially starting at the right side of the graph is when your nuclei are far apart. When they're too far apart, they don't really feel each other, which is why the graph is close to zero here. There is essentially no interaction between your two nuclei. But as you move them closer and closer together, the energy starts to drop because those two atoms are attracted to one another if they're going to form a bond. So as they get more and more attracted to one another, you get down to this minimum point, which is the most stable state. If you push the nuclei even closer together, it starts to turn back up because the protons in one nucleus and the protons in the other nucleus start to repel one another more strongly. So there is attractive force between the electrons on one atom and the nucleus of another, which is what creates the bond. But there's also repulsive forces between the two nuclei themselves, and this energy minimum is where those forces balance each other out. That the attractive forces and the repulsive forces are in balance, so your nuclei don't move. They stay at that distance. So this distance to this most stable state represents the length of the bond between two atoms. The energy of that attraction is how much energy you would have to put in order to completely separate those atoms. So the distance on the y-axis from 0 down to that minimum is the bond strength. So essentially, the deeper your well here, the stronger the bond, the positioning on the x-axis is telling you the length of the bond. If it's farther to the left, it's a short bond. Farther to the right is a long bond. So if we consider what the question was actually asking us here, we were given 3 of these graphs on the same set of axes and asked to identify which one's hydrogen, which one's nitrogen, which one's oxygen. So we can see that we have 2 bonds that are kind of similar in length, 2 bonds that are kind of similar in strength. This one is much shorter than the other 2. This one is much stronger than the other 2. So what we want to think about is kind of what affects length, what affects strength, and how do those relate to the structures of hydrogen, nitrogen, and oxygen molecules. So in terms of length, really in terms of both length and strength, there are 2 things to consider, and that is the size of the atoms themselves and whether they're double, single, or triple bonded together. So smaller atoms make shorter bonds. That should make some sense. So in this case, of the options that we are given, nitrogen and oxygen are right next to each other on the periodic table, so they're going to be really similar in radius, but hydrogen is a row above them, which means it's going to be a lot smaller. So smaller atoms make shorter bonds, so it is a reasonable assumption to make that this bond here that is much shorter than the other 2 is probably going to be hydrogen, because the atoms of hydrogen are just so teeny that they're going to form a shorter bond. Then between these other 2, we have a big difference in strength, and strength is also related to length to an extent, and therefore to atomic size to an extent. But if we're looking at 2 elements of similar size, the big difference in strength is going to come between, is it a single bond, a double bond, or a triple bond? More bonds makes a stronger attraction. So looking at the structures of these 2 things, we see oxygen is a double bond, nitrogen is a triple bond, so we expect that triple bond to be stronger. Since these 2 things are similar in radius. So it is reasonable to assume that the strongest bond of these 3, the deepest well, is going to be nitrogen because it's got a triple bond. The shortest bond, the one farthest to the left, is probably hydrogen because those atoms are just so much tinier than the other elements we're dealing with here, which means this guy must be oxygen. So A is the correct choice on that one. And last but not least, you were asked to rank the following compounds in order of increasing lattice energy. Lattice energy is another thing to add to our list of things governed by Coulomb's law. So lattice energy is essentially just the strength of ionic bonds. And ions are charged particles, so the strength of attraction between charged particles is going to be controlled by Coulomb's law. So as usual, we have the same 2 big factors involved in Coulomb's law, which are the size of the charge and the distance between the charges. So the larger the charges on the ions, the stronger the attraction is going to be, therefore the greater the lattice energy, and the smaller the radius of the ions, is meaning the closer the charges are together, the stronger the attraction will be, or the greater the lattice energy. So the highest one is probably the easiest to figure out, is going to be the magnesium oxide, because that has +2 and -2 charges, so the greater charge is usually the more important factor here. So since we have plus and minus 2 charges for both of our ions, that's going to get us a stronger attraction. Magnesium chloride would be the next highest, since it has a +2 with a -1, and our other 2 compounds are both +1, -1 combinations. So the 2 lowest charges are going to be the 2 lowest lattice energies. Increasing one charge is going to make your lattice energy higher. Increasing the other charge as well is also going to make it even higher. Between these 2, where we have the same combination of charges on our ions, is where we want to consider the radius. You were given radius data here for precisely this reason. And we can see from this data that fluorine is smaller than chlorine. Fluoride is smaller than chloride, and smaller ions make stronger attractions. So the larger ion would be the weakest here, then this one. It's also important to note that sodium and magnesium are relatively similar in size, so that means that the radius is not really a determining factor in like this distinction here, that these two are pretty similar in size, so the fact that magnesium has a higher charge is going to be like definitely the most important thing. Usually charge is the bigger factor here. But you should be able to rank these in terms of ionic bond strength, and hopefully that's familiar from Chem 2. So that's all for today.